In this module, we will cover the flight instruments system of the ATR. We will start out with a brief system description. Next, we will look at the individual components of the flight instruments systems. These subsystems consist of the air data computers, the Attitude and Heading Reference System, or AHRS, the Electronic Flight Instrument System, or EFIS, the flight recorders, and the aircraft clocks. Numerous aircraft systems require air data information such as airspeed, vertical speed, and pitot static pressure values. This information is provided by the Air Data Computers, or ADC. An Attitude and Heading Reference System, or AHRS, provides attitude and heading information to various subsystems. For example, the radar antenna is stabilized by using attitude information that is provided by the AHRS. The EFIS system processes the information from various sources and displays it to the crews through the ADIs and EHSIs. Since everything in aviation is time-related, the aircraft is equipped with two clocks. There is one clock located on each side of the flight instruments panel. The aircraft is equipped with a cockpit voice recorder, or CVR, and a digital flight data recorder, or DFDR. The cockpit voice recorder records audio from the flight deck. Audio is collected from an area microphone as well as through each remote-controlled audio unit, or RCAU. Various aircraft parameters are also automatically recorded by the digital flight data recorder. The ATR is equipped with 3 independent air data systems. There are 2 main systems and 1 standby system. The air data computers are powered by the DC emergency bus and are backed up by the hot emergency battery bus. Each air data computer receives static air pressure, total air pressure, and total air temperature through a dedicated static port, pitot static tube, and total air temperature probe. These probes are located on the left and right side of the forward fuselage and are electrically heated. The information provided by these probes is processed by each air data computer. Each air data computer then calculates pressure altitude, vertical speed, indicated airspeed, true airspeed, total air temperature, and static air temperature. Each ADC then supplies altitude, speed, and vertical speed information to the associated flight instruments. ADC 1 controls information on the captain's instruments, and ADC 2 controls the first officer's instruments. ADC 1 also supplies information to AHRS 1, the Flight Data Acquisition Unit, the GPWS system, the pressurization system, the automatic flight control system, the MFC, and the transponder system. ADC-2 also supplies information to AHRS-2, the Flight Data Acquisition Unit, the MFC, the pressurization system, the automatic flight control system, and the transponder system. Some systems require that the ADC source be specifically selected by the ADC source selector switch on the captain's side of the flight instruments panel. These systems include the engine EECs, the total air temperature, static air temperature, true airspeed indicator, and the GPS system. The standby system consists of 2 static ports and a pitot tube. The standby static ports are located on either side of the forward fuselage, whereas the standby pitot tube is located on the left side of the aircraft. These probes directly supply airspeed and altitude information to the standby airspeed indicator and the standby altimeter. The standby instruments function as traditional pressure instruments and do not rely on the ADC. The airspeed computed by the air data computers is displayed on an associated indicated airspeed indicator. Each ADC corrects static source position errors as airspeed varies. As a result, indicated airspeed is sometimes referred to as computed airspeed. There are two airspeed indicators on each side of the flight instruments panel. The captain's airspeed indicator is powered by the 26 volts AC standby bus. The first officer's airspeed indicator is powered by the 26 volts AC bus 2. A barber pole indicates the maximum airspeed computed by the associated air data computer. In the event the aircraft exceeds this limit, the central crew alerting system will generate a clacker sound to alert the crew. An internal speed reference bug can be set by the speed selector knob located on the bottom right-hand side of the airspeed indicator. Your company policies and procedures will dictate how this airspeed bug is used. Each electronic attitude director indicator has a fast-slow indicator. This indicator reflects the aircraft's speed with respect to the airspeed bug set in the airspeed indicator. For example, if the aircraft's airspeed is greater than the speed selected by the speed bug, then the associated fast-slow pointer will be in the fast range. There are 4 plastic speed bugs on the outside of the airspeed indicator. These speed bugs are manually moved and can be used to mark additional airspeeds. Once again, the use of these speed bugs is dictated by your company policies. The airspeed indicators have 2 failure flags. The red VMO flag is displayed when there is a failure in the VMO channel. The red off flag is displayed when there is a failure of the airspeed indicator and the VMO channel or a loss of AC power. A standby airspeed indicator is located on the left side of the instruments panel. This standby airspeed indicator is entirely driven by the standby pitot static system and requires no electrical power. The standby airspeed indicator displays speed in 5-knot increments from 40 to 200 knots and 10-knot increments from 200 to 320 knots. There are no bugs or VMO/MMO indicators. There are 2 altimeters located on either side of the flight instruments panel. These altimeters display the altitude calculated by the associated air data computer. The captain's altimeter is powered by the 26 volts AC standby bus, and the first officer's altimeter is powered by the 26 volts AC bus 2. The altimeter's barometric reference is changed by the barometric knob in the lower left-hand corner of the altimeter. The select barometric setting is displayed in both inches of mercury and hectopascals in the barometric setting window. The aircraft's altitude is displayed in the altitude counter window. 4 drums are used to display the aircraft's altitude in 10,000, 1,000, 100, and 20 feet increments, respectively. When the aircraft's altitude is below 10,000 feet, the leftmost drum displays a black and white flag. The 2 leftmost digits of the digital counter indicate a negative when the aircraft's altitude is below sea level. In addition to the altitude counter, The altimeter has a pointer which rotates as the aircraft's altitude changes. One revolution of the pointer represents a 1,000-foot change in altitude. The altitude alert light illuminates when the altitude alert is triggered. The altitude alert is triggered when the aircraft's altitude is within 1,000 feet of the altitude selected in the ADU. The altitude alert light extinguishes when the aircraft's altitude is within 250 feet of the selected altitude. A momentary aural alert sounds when the altitude alert light illuminates or extinguishes. An off flag is displayed over the altitude counter anytime there is a power failure, the associated air data computer has failed, or the indicator displays erroneous information. A standby altimeter is located on the left side of the Flight Instruments panel. This instrument is driven by the standby static system. It does not require electrical power to operate. However, this standby altimeter does incorporate an electrical vibrator to ensure that the friction between the parts within the altimeter does not cause the altimeter reading to hang. This electrical vibrator is powered by DC bus 1. The standby altimeter has 3 drums to indicate the aircraft's altitude in 10,000, 1,000, and 100-foot increments. A pointer provides a more precise indication of the aircraft's altitude in 20-foot increments. One revolution of the pointer represents 1,000 feet. When the aircraft's altitude is below 10,000 feet MSL, the leftmost drum is covered by a black and white flag. When the aircraft's altitude is below sea level, the 2 leftmost drums are covered by an orange and white flag. The barometric setting of the standby altimeter is set by means of the barometric set knob in the bottom left-hand corner of the standby altimeter. The barometric setting for the standby altimeter can be set in inches of mercury or millibars depending upon the installation. The standby altimeter is driven by the standby static pressure system. The regular altimeters are driven by the associated air data computers, which process data from the pitot-static system and provide the associated altimeters with a refined and calibrated reading. Therefore, you'll notice in flight that there may be altitude differences between the standby altimeter and the 2 regular altimeters. The chart displayed here indicates the various tolerance levels. The aircraft's vertical speed is displayed on 2 liquid crystal displays located on either side of the Flight Instruments panel. This indicator is used to indicate the aircraft's vertical speed as well as any TCAS resolution advisories. The captain's vertical speed indicator is powered by the 26 volts AC standby bus, and the first officer's vertical speed indicator is powered by the 26 volts AC bus 2. A light sensor adjusts the brightness of the display based on ambient conditions. The brightness can also be adjusted by the instrument brightness control knob on the lights panel located on the center pedestal. The VSI pointer indicates the aircraft's vertical speed in feet per minute. The vertical speed indicator can indicate rates of climb or descent between 0 and 6,000 feet per minute. A vertical speed flag is displayed when there is a failure of the vertical speed indicator. In this case, the pointer will also be removed from view. Vertical speed indications are generated by the air data computer based on rate of altitude change only. It is not an IVSI type of indicator. The vertical speed indicator is used to display TCAS-related information. The TCAS is discussed in the TCAS module, and therefore the information will not be covered here. The aircraft's true airspeed is displayed on the true airspeed temperature indicator located on the captain's side of the flight instruments panel. The air data computer selected by the ADC switch is used to calculate the true airspeed. If the true airspeed display shows amber dashes, it indicates that the selected air data computer is producing an invalid signal. This indicator can display values between 68 and 600 knots. The total air temperature is displayed to the left of the true airspeed indicator. The temperature is displayed in degrees Celsius only. 3 amber dashes indicate that the selected air data computer is calculating an invalid total air temperature value. The static air temperature push button enables the crew to display the static air temperature in degrees Celsius. The static air temperature value is displayed in the total air temperature window. Static air temperature is equal to the actual outside air temperature. Total air temperature is the temperature actually sensed by the temperature probe while in flight. When stationary on the ground, total air temperature will equal static air temperature. The ADC selector switch is used to select the air data computer, which will supply information to the EECs, the total air temperature true airspeed indicator, and the GPS if one is installed. The fault light above the switch illuminates in the event the selected ADC disagrees with the ADC selector switch position. Attitude and heading reference information is provided by the Attitude and Heading Reference System, or AHRS. The aircraft is equipped with 2 AHRS systems. In addition, there is a standby system in the event of a failure of both AHRS systems. In addition to the remote compass systems in each wing, the AHRS system includes 2 attitude heading reference units which are strapped down to the floor of the forward cargo compartment. Each AHRU remains operational throughout 360 degrees of bank and 90 degrees of pitch. They also provide the system with automatic compensation for the Earth's rotation and gyro drift without manual insertion of heading, latitude, or variation. AHRS-1 is powered by the DC emergency bus. DC Bus 2 provides an auxiliary power supply to AHRS-1. AHRS-2 is powered by DC Bus 2. It also has an auxiliary power supply which changes depending on whether the aircraft is on the ground or in flight. On the ground, the auxiliary power supply for AHRS-2 is the DC emergency bus. In flight, the auxiliary power supply is from DC Bus 1. The AHRS consists of 2 attitude heading reference units, or AHRU, 2 flux valves, and 1 dual remote compensator. The attitude heading reference unit consists of an inertial measurement unit, a microprocessor, and a control system. The inertial measurement unit incorporates a gyro system and 3 accelerometers aligned with 3 aircraft axes. The gyro system and accelerometers provide information so that the microprocessor can calculate the aircraft's movement in space. The attitude heading reference unit consists of an inertial measurement unit, a microprocessor, and a control system. The inertial measurement unit incorporates a gyro system and 3 accelerometers aligned with 3 aircraft axes. The gyro system and accelerometers provide information so that the microprocessor can calculate the aircraft's movement in space. The 2 flux valves provide magnetic heading information to the associated AHRU. The flux valves are located in each wingtip. The AHRU calculates attitude and heading information, which is then supplied to the various flight deck indicators, the automatic flight control system, the weather radar, and the flight data acquisition unit. AHRS-1 supplies attitude and heading information to the number 1 symbol generator unit, the first officer's RMI, the flight data acquisition unit, and the radar. The radar is only supplied with attitude information in order to stabilize the radar antenna. AHRS-2 supplies attitude and heading information to the number 2 symbol generator unit and the captain's RMI. Each AHRS is coupled to the opposite RMI. The AHRS drives the compass card and the aircraft's heading is indicated by the heading pointer. A red off flag is displayed in the event of a loss of the associated AHRS data or if there is an internal failure of the associated RMI. The AHRS system incorporates an auto-erect function which uses the true airspeed information from the air data computer. In the event this true airspeed signal is lost, the affected AHRS will continue to operate but without the auto-erect function. The loss of the true airspeed information will result in the illumination of the auto-erect fail light on the affected side of the Flight Instruments panel. If the true airspeed signal is lost, the system reverts to what is known as the AHRS basic mode. The affected AHRS can still be erected while in flight. This is not recommended typically since it will require that the aircraft be in unaccelerated level flight. The affected AHRS is erected by pushing and holding for 15 seconds the AHRS erect push button on the affected side. When the aircraft powers up, the AHRS system needs about 3 minutes to initialize. While it is initializing, the attitude fail and heading fail flags will appear on the EADI and EHSI. The time remaining for initialization can be determined by pressing the respective AHRS button. At the beginning of the process, the compass card will indicate 180 degrees to indicate 180 seconds left in the process. From there, the compass will decrease 1 degree per second until it shows 0. Standby instruments provide an alternate source of attitude and heading information in the event there is a failure of both AHRS systems. Standby attitude information is provided by the standby attitude indicator and the standby compass. The standby attitude indicator is located on the left side of the Flight Instruments panel. This unit consists of a single gyroscope which provides the attitude information. This gyroscope is spun by a motor which is powered by the DC essential bus. The hot emergency battery bus is the alternate source of power for the standby attitude indicator. On emergency battery power only, the aircraft systems have about 20 or 30 minutes of life remaining. After that, the standby ADI will begin slowly tumbling as the gyro starts to spin down. A red and white flag is visible in the standby attitude indicator in the event there is a loss of power or when the speed of the gyroscope is insufficient to provide a reliable attitude indication. When the aircraft is initially powered, the gyroscope needs to be manually erected by pulling on the setting knob. Rotating the knob without pulling it out aligns the aircraft symbol with the artificial horizon of the standby attitude indicator. Standby heading information is provided by a retractable magnetic compass. The compass is extended or retracted by the slider switch. This compass does not require any electrical power in order to operate. An electronic flight instrument system, or EFIS, processes data from various sources and displays the information on the 4 flight deck CRTs. Information is provided to the EFIS system from the AHRS, ASI, and the navigation system. Each pilot station has 2 CRTs that display attitude and navigation information. The top CRT is called the Electronic Attitude Director Indicator, or EADI, and the bottom CRT is called the EHSI, or Electronic Horizontal Situation Indicator. The CRTs incorporate a light sensor which automatically adjusts the brightness of the associated screen to account for ambient conditions. 2 symbol generators process data received from various systems into video signals which are then displayed on the EADIs and EHSIs. Each symbol generator receives inputs from the associated DME, ADF, nav system, AHRS 1 and 2 through the avionics standard communication bus. This bus collects information and passes it to the systems that require the data. The symbol generator then converts this information into the required video signal. The SGU forms all the symbols, alphanumeric text, and colors displayed on the CRTs. Normally, the SGU supplies the on-side EADI and EHSI, but because the ASCB has all the data portrayed on either CRT screen, either SGU can supply 4 CRTs if necessary. The symbol generator converts signals from the automatic flight control system and displays the commands in the form of flight director bars. The flight director bars are selected or removed from view by means of 2 flight director switches located on either side of the glare shield. Each switch controls the flight director bars on the associated EADI. Course and heading selections are additional inputs into the symbol generators. This information is then displayed on the EHSIs. Course and heading selections are made on the course heading panel. The selected course is displayed on the associated EHSI. However, the selected heading is displayed on both EHSIs. The first officer can also select a course which is then displayed on the first officer's EHSI. This arrangement allows both crew members to select different courses. The weather control panel is used to select the range scale of the EHSI. Weather returns are only displayed in the ARC mode. An EFIS control panel is located on the center pedestal. This panel enables the crew to select the desired EFIS mode as well as adjust the brightness of the screens. The full arc push button controls the presentation on the EHSI. Pressing the button switches between the full mode and the arc mode. This panel is interactive, so you can press the full arc mode to see the effects. The ADI DIM Decision Height Test knob consists of an inner and an outer knob. The inner knob is used to set the decision height, which is then displayed in blue on the electronic attitude director indicators. The white DH letters identify the selected decision height. A decision height between -10 feet and 990 feet can be selected by this knob. The decision height is cleared from the EADI by selecting a value of 0. This removes the white DH letters as well as the decision height that was previously selected. The EFIS and radial altimeters are tested by pressing on the inner knob. The EFIS portion of the test only works on the ground, but the radial altimeter test works at all times. The EFIS test results in the display of all failure messages on the EFIS displays. The radial altimeter test results in a radial altitude of 100 feet, which is displayed on the EADI. The outer knob turns the associated electronic attitude director indicator on or off. Once the knob is out of the off position, the brightness of the associated electronic attitude director indicator can be adjusted by rotating the outer knob. The HSI DIM weather knob also consists of an inner and an outer knob. The outer knob turns the associated EHSI on or off. Turning the EHSI off selects the composite mode where all screen information is portrayed on the electronic attitude director indicator. Once the knob is out of the off position, the associated EHSI screen brightness can be adjusted by rotating the knob. The inner knob is used to show or hide the weather radar returns on the associated EHSI. Weather radar returns are not displayed when this knob is in the off position. Once out of the off position, the knob can be used to adjust the brightness of the weather radar returns independently of the EHSI brightness selection. The RNAV track, VOR or ADF course can be selected or removed from the EHSI by means of the associated bearing selector. The pointer is removed from view on the associated EHSI by selecting the off position. Since there are 2 bearing selectors on each EFIS control panel, each crew member can display their own bearing information as well as the offside bearing information. The bearing information from the left side is displayed in blue, and the bearing information from the right side is displayed in green. The map push button alternates between the map display and the arc display on the associated EHSI. In the map mode, the flight plan waypoints are displayed on the associated EHSI. The active waypoint is displayed in magenta. The other waypoints are displayed in white. The VOR localizer push button selects the VOR localizer mode on the associated EHSI. The GPS mode is selected on the EHSI by pressing the RNAV push button. The ground speed time to go push button alternately displays on the EHSI the aircraft's ground speed or time to go. The EHSI automatically defaults to the ground speed mode at power up. In the event of a failure, A switching system enables each crew member to connect their displays to the opposite side's source. Failures of the attitude information, heading, VOR or ILS, or a malfunctioning symbol generator unit are handled by means of the two switching panels. There is a switching panel on each side of the Flight Instruments panel. A failure of one AHRS system is indicated by the removal of the attitude and heading information from the EADI and the EHSI. The EADI will display a red attitude failure message. The EHSI will display a red heading failure message at the top of the EHSI. In this situation, the attitude heading push button enables a crew member to select the opposite AHRS as the source for the EADI and EHSI. When the switch is pressed in, the system light illuminates to indicate that the EADI and EHSI on that side are using the opposite AHRS as the source. In this example, AHRS1 has malfunctioned, so the AHRS needs to be switched. Click on the Captain's Attitude heading push button to continue. After the captain has pressed the attitude heading push button, the System 2 caption illuminates white, indicating that the captain's EADI and EHSI are now driven by AHRS2. On the first officer's attitude heading push button, the Captain 2 caption illuminates green to indicate that the captain's EADI and EHSI are operating off the data from AHRS2. Once the switching has occurred, both EADIs will indicate the source of the information. In the example used so far, both EADIs will indicate an amber Attitude 2 message in the upper left-hand corner of the screen to indicate that AHRS2 is now providing attitude information to the EADI. In addition, the EADI will also indicate an amber Heading 2 message. If the VOR or ILS source fails, the EADI will display a red cross over the glide slope deviation indicator if ILS is selected. In addition, there will be a red cross over the lateral deviation indicator. The EHSI will also display failure indications which consist of a red cross over the vertical deviation indicator, a red cross over the lateral deviation indicator, and amber dashes for the course and distance indications. In the same manner, each side can select VOR or ILS information from the opposite receiver. The VOR-ILS push button controls this switching function. When a VOR-ILS push button is pressed, the system caption illuminates green to indicate that the VOR-ILS on this side is derived from the opposite side. On the opposite VOR-ILS push button, the top caption illuminates to indicate that the opposite crew member is using that side's VOR-ILS information. In this example, the captain's VOR-ILS is derived from VOR-ILS2. The System 2 caption is illuminated on the captain's VOR-ILS push button, and the first officer's VOR-ILS push button has an illuminated Captain 2 light. After the VOR-ILS source has been switched, both EHSIs will display an amber message in the upper right-hand corner of each EHSI. The possible messages are VOR1, ILS1, VOR2, or ILS2. An SGU failure is indicated by the removal of all information from the affected side's EHSI and EADI. In addition, the displays will display a red cross along with a red symbol generator failure message. The symbol generators can be switched in the same manner by using the EFIS symbol generator push buttons. When the push button is pressed, the system caption illuminates on the side that's being switched, and the crew position illuminates on the opposite symbol generator push button. In this example, the captain has switched the symbol generator. The System 2 caption illuminates white, and the Captain 2 caption on the first officer's push button illuminates green. Once a symbol generator source has been switched, both EADIs will display in amber the new symbol generator source. In this example, both EADIs are displaying an amber symbol generator 2 on the left-hand side of both EADIs. There is another type of switching that occurs when a CRT is turned off. If either the EADI or the EHSI is turned off, the remaining CRT will display both EADI and EHSI information in the composite mode. You can click on the EADI knob to turn the EADI off or on. The symbol generators compare the information derived from both AHRS and ILS systems. When a symbol generator detects a significant difference, it will trigger a CCAS warning. This warning consists of an illuminated EFIS comparator light on the crew alerting panel and the flashing of both master caution lights. In addition, a single chime will sound. The data that causes the comparator alert to trigger is identified on the EADI. If the two AHRS heading differ by more than 6 degrees at bank angles below 6 degrees, the amber heading message is displayed. If the bank angle is greater than 6 degrees, the tolerance level increases to 12 degrees. If the two AHRS pitch or roll values differ by more than 6 degrees, the EADIs will display either an amber pitch or roll message. If both pitch and roll values differ by more than 6 degrees, the EADIs will display an amber attitude message instead. If the localizer value from both ILS systems differ by more than 0.6 degrees, both EADIs will display an amber localizer message. If the glide slope value from both ILS systems differ by more than 0.2 degrees, both EADIs will display an amber glide slope message. If both the localizer and glide slope values differ by more than 0.6 degrees for the localizer and 0.2 degrees for the glide slope, both EADIs will display an amber ILS message. The ATR is equipped with a cockpit voice recorder and a digital flight data recorder. The two recorders are automatically powered and start recording when the aircraft is operating on its own electrical power. The two recorders automatically shut down 10 minutes after the engines have been shut down. If the aircraft is powered by an external ground power cart, the recorders are off until one engine is operating. Each recorder incorporates an underwater acoustic beacon. Beacon actuation occurs when the recorder is immersed in water. The effective range of the acoustic beacon is 3.5 kilometers. Once activated, the beacon is designed to operate continuously for a period of 30 days. The cockpit voice recorder, or CVR, continuously records all communications that pass through the remote control audio unit. The CVR will also record cabin crew announcements. In addition, the CVR will also record flight deck audio through an area microphone located below the overhead panel. This microphone will also record audio alerts. At all times, the cockpit voice recorder only retains the last 30 minutes of recordings. The Flight Data Acquisition Unit collects information from various aircraft systems and converts them into digital format. The Digital Flight Data Recorder records the digital data produced by the Flight Data Acquisition Unit. At all times, the DFDR only retains the last 25 hours of recordings. The Cockpit Voice Recorder panel, located on the overhead panel, is used to test the CVR as well as erase any information stored by the Cockpit Voice Recorder. The Cockpit Voice Recorder tape can be erased by pressing the Erase push button. The tape will be erased provided the landing gear shock absorbers are compressed and the parking brake is set. The tape is completely erased by pressing and holding the Erase push button for 2 seconds. The CVR is tested by pressing and holding the Test push button. This activates the test circuit and the pointer in the adjacent indicator moves to between 8 and 10. If a headset is plugged into the panel, a 600 Hz tone will be heard through the headset. Movement of the pointer into the white band area indicates a successful test of the Cockpit Voice Recorder. A Flight Data Entry panel, located on the center pedestal, enables the crew to make limited inputs into the Digital Flight Data Recorder. The Flight Data Entry panel enables the crew to set the flight number as well as set an event mark on the DFDR recording. The status of the Flight Data Acquisition Unit is indicated by the status FDAU light. Illumination of this light indicates a failure of the Flight Data Acquisition Unit. The status of the Digital Flight Data Recorder is indicated by the status system light. Illumination of this light indicates a failure of the Digital Flight Data Recorder or a loss of power to the DFDR. The recorder push button on the center pedestal energizes both the Cockpit Voice Recorder and the Digital Flight Data Recorder. Both systems will operate normally. This is the manual mode of operation. When the manual mode is enabled, the blue on caption illuminates in the push button. The manual mode is disabled by pressing the Reset push button. There are 2 clocks located on either side of the Flight Instruments panel. The captain's clock is powered by the DC emergency bus. The first officer's clock is powered by DC bus 2. Each clock incorporates an internal battery which maintains the time function of each clock while the aircraft is unpowered. Time is indicated in hours and minutes by 2 pointers. The clock is designed to operate as a chronometer as well. The chronometer time is indicated in minutes and seconds by 2 additional pointers. The seconds pointer makes 1 revolution per minute. The minutes pointer makes 1 revolution per hour. The chronometer function is controlled by the chronometer push button. The push button is used to start, stop, and reset the chronometer. The first push starts the chronometer. The second push stops the chronometer. The third push resets the chronometer. The clock time is set by pulling and rotating the time knob. This concludes the Flight Instruments module.